Hello, welcome back to this video again. We're going to proceed with the fatty acids so that we go in details for each of them. So we said we have two types of fatty acids. So firstly, we're going to look at saturated ones, saturated fatty acids. So these they are characterized by having single carbon to carbon bonds. So these are flexible. These are rigid. So since they are rigid, this means that they are solids at room temperature. So these saturated fatty acids, they are solids at room temperature. They have a maximum number of hydrogen atoms. Maximum hydrogen atoms. One example of a saturated fatty acid is that of stearic acid. So the molecular formula for stearic acid, let's write it so that we draw the structure for stearic acid as an example. So we have CH3, CH3, then CH2, then close. We have 16, and we have this. So this means that we have how many number of carbon atoms? So meaning we have 18 carbons in total. 18 carbons. And what else? We have how many hydrogens? So we have 3 and 16 by 2. We have 32. 32 plus 6. We have 38 hydrogens. Then we have 2 oxygens. So let's draw the structure now. So stearic acid is actually found in butter. We also find it in cheese. Then we also find it in coconut oil. Coconut oil. Also in meat. In margarine. And also in fried foods. So that's where you find these saturated fatty acids. So let's draw the structure now of this steric fatty acid. So we have one carbon, and two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Then lastly we have 18. So the rest we have hydrogen atoms. So this is the tail that we are talking about, since it is hydrophobic. We just have a long hydrocarbon, a long chain of hydrocarbon. So from here all the way up to here. So this is what we call the tail of this. But here, this part here, this portion here, this is the head. So that's the one that we're calling the polar head. Polar. But here it's non-polar. Non-polar. So let's go now to the other structure for the unsaturated fatty acid that has got double bonds, which is deficient of the hydrogens. So for these, they have double bonds, carbon carbon double bonds. So these, they are flexible, unlike the saturated ones which are rigid. So these, they are liquids at room temperature. So this means that these, they are flexible at this same double bonds. Because of these double bonds, that's why they are flexible. So we said they're deficient of hydrogen atoms. So this means that they don't have the maximum of number of hydrogen atoms as compared to the saturated ones. So an example of these, we have oleic acid. Oleic acid is one example. So this oleic acid has got this molecular formula CH3 CH2. We have a 7 here. Then we have CH, and we have a double bond here. Another CH here. We have CH2. So 7. Then we have the head here. So as we can see, how many number of hydrogen, I mean of carbons, can we count from this structure here? So we have 2 times 7, we have 14. Again here 2 times 7, we have 40. So 14 plus 14, we have 28. So 28 plus these two here, this one and this one. So we have 30. Then plus this one and this one, now we have, so 32 carbons. What about for hydrogens? So we have the same here. So here, no, not 32 carbons. So we have here 7 plus this 7, we have 14. Then plus this 2, we have 16. Plus this 2, we have 18. So 18 carbons. 18 carbons. Then hydrogens, we have 14 plus 14, which is 28, plus this one here 29, plus this one here 30, plus this one 31, plus this 3 here, we have 34. So let's draw the structure now for oleic acid. So for the structure of oleic acid, we have, so let's draw up to 18 carbons. So 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have the double bond 1, 2, 3, 4, 5, 6, 7, 8, 9. Between position 9 and 10, that's where we have the double bonds 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have the double bond there. So let's now put the number of hydrogen atoms that are remaining for each of these. So we have hydrogen, we have hydrogen, we have hydrogen, we have hydrogen here, here, here. So as we already said earlier, this is the head, which is the polar, and from here all the way to this other side we have the tail, which is non-polar. So this is oleic acid, which is unsaturated fat acid. Yeah, so this is oleic acid. So fat acids are actually can be called cis or trans according to how you put the hydrogen bonds on this double bond here. So when you have hydrogen bonds being put across on the one side, we call it cis. So like this one, it's a cis because of these hydrogen bonds since they are on the same sides. So this hydrogen and this hydrogen. So this is a cis. But when the hydrogen, for example, if we were to put this one here on the other side here, so this one will be a trans since hydrogens are on opposite sides. So let me just write it somewhere so that you don't get confused. Some students get confused when you give an example here. They'll think maybe that's how it is for the structure. So we have, for example, this one. So we have this hydrogen here. We have this hydrogen here. So this one we call it a cis double bond. So same side. So but when you have this one here, when you have another hydrogen this side and the other hydrogen on the opposite side, so this one I call trans double bond. Okay, let's go now to the structure of glycerol. So the next type of lipid is a glycerol. Since we're just from looking at fatty acids, let's go to the next one now, which we call glycerol. So glycerol is just a simple lipid which has got 3 carbons. So the structure of glycerol is like this. So we have one carbon, another carbon, another carbon. So this is the structure of glycerol. And this side we have hydrogens. We do have a hydrogen, and also this side we have hydrogen. So this is just an alcohol. This is a 3 carbon alcohol. Polyalcohol. So this is the one that combines with the fatty acids to form glyceride lipids or glycerides combine with the fatty acids to form glycerides. So what do we mean by this? So we mean when we have a fat acid plus glycerol, we are going to have glyceride. Yeah, so that's what we mean here. So this one is just produced from lipids. So glyceride produced by the process that we call saponification. Let's even underline it. Saponification. So reaction between sodium and the glycerides. Glycerides. So it is used as a solvent, as a sweetener, so additive, as an additive in food, and also used for preservation of foods, also in the pharmaceutical industries in making drugs. So thank you for watching this video. In the next one, we are going now to go into details looking at the glycerides. Thank you. Subscribe to the channel.